How you doing, everybody? Mr. Kolakowski here. I'm going to go through three sample problems with the wave speed equation, and let's see how this goes. I'm using this pen feature for the first time, so please be patient if it takes me some fumbles to get through and figure out how to kind of get this to work just the way I'm thinking it can. All right, the first sample problem here is this is from chapter 19.4. If a train of freight cars, each 10 meters long, rolls by you at the rate of 3 cars each second, what is the speed of the train? Okay, this is a question about speed. Now, back in the first semester, we would have used something as simple as a distance per unit time. This is a little bit different, I think, because this involves frequency. Um, I suppose it's assumed that you've read through chapters 19.1 through 19.3 already, and you know a little bit about waves. You can solve this problem a couple of different ways. I think the easiest way to do it is with the equation. Let's see here. So I want um, the pen feature. Let's see if I can get this to work. All right, so V equals F times lambda. So for this particular problem, we know that the frequency here is 3 cars each second. So 3 hertz is the frequency. What does that really mean? 3 hertz means 3 cycles per second. Um, Cycles is just a count. It's not a unit of frequency. So let's go ahead and fill this into the equation. We're trying to find the speed of the train, which in this case, wave speed is equal to frequency times wavelength. So the frequency is going to be 3 per second. That's what hertz means, is cycles per second. Um, I suppose it looks a little bit funny to write it that way. You could just say 3 hertz, but I'm writing it out as 3 cars per second. We're going to multiply that by the wavelength, which they have told us is 10 meters right here. So when we go ahead and plug this into the equation, we're going to find out you get meters over seconds. The correct answer is 30 meters per second. Um, Frequency, I think, was our telltale sign here that we could use the wave equation for this problem, and hopefully that one makes sense. All right, on to the next sample problem. Let's see how that one plays out. Number 2 says, if if a water wave isolates, sorry, okay, I'm trying to do two things at once here. If a water wave oscillates up and down 3 times each second and the distance between the wave crests is 2 meters, what is its frequency? What is its wavelength? And what is its wave speed? Um, okay, so fundamentally they're looking for the wave speed for this water wave. Okay, so first of all, they say it oscillates up and down 3 times each second. So for us, coincidentally, that means the frequency here is 3 hertz, which again, hertz means 3 waves per second. Um, if we remember from the previous problem, V equals F lambda, we can use that equation. Let me go ahead and kind of put that over here a little bit. That's the frequency. Let's multiply that by the wavelength. Well, they tell us that the distance between the wave crests is 2 meters. The distance from crest to crest is wavelength. So here we're just going to multiply this by the 2 meters of wavelength, and that's going to give us 6 meters per second. Not too bad. I hope that one makes sense. Let's move on to the last sample problem here. Okay. This one's a little more difficult. It says the speed of light is 3 times 10 to the 8th meters per second. Orange light in the visible part of the electromagnetic spectrum has a wavelength of 5.9 times 10 to the negative 7 meters. So orange light has a really, really small wavelength compared to water waves and things like that. What is the frequency of orange light? Okay, Well, let's start with this equation, v equals f lambda. Now, the first thing we notice is they're asking us to solve for frequency this time. One thing I can do is divide both sides by wavelength and find out here that frequency is wave speed divided by wavelength. Okay, that's frequency. All right, so let's plug in what we know. We have the speed of light in meters per second, 3 times 10 to the 8th. We're going to divide by the wavelength of orange light, which is 5.9 times 10 to the negative 7 meters. Now, just looking at units, when you take meters per second, uh, a unit of meters per second and divide it by meters, what's going to happen is you're going to cancel out the meters. You're going to get cycles per second, which is frequency. Okay, you're going to need your scientific calculator for this. The way I would type this in is I'll write it over here. You would do 3 exponent 8 divided by 5.9 exponent negative 7. Now that exponent button is just something that you use in your calculator. It's not something to use when you're communicating scientific notation, but it is the way that we use our scientific calculators to use powers of 10 like that. So anyway, when you put this in your calculator, I figured this out just a little bit ago. It's 5.08 times 10 to the 14th cycles per second over you could put this over seconds, but really that just means hertz. And there we go. This is the frequency of orange light. Now you would imagine different colors of light have different frequencies. Well, that's exactly what occurs. Higher energy light, like blue light, for example, has a higher frequency. Lower energy light, like red light, has a lower frequency. That's something we'll learn about as we get further along in the semester. But for right now, the base equation was V equals F lambda, and we were able to solve for frequency of orange light in this particular case. So let me go ahead and scroll back up. Samples 1 and 2 are found in the textbook on page 363. If you're using your e-textbook, those 2 sample problems are at the end of section 19.4, which is called wave speed. And if you have any questions, don't hesitate to let me know. I hope you guys are doing great. This is a crazy time. Hang in there, and we'll get through this together, all right? I hope you guys are healthy. Talk to you soon. Bye-bye for now.